All right, so welcome to the part 2 of this tutorial on the topic of feedback amplifier. So we have seen in our previous module what is a feedback amplifier, what it does, and the definition of negative feedback and the positive feedback. And in our one of our previous module, we talked about these configurations out of the 4 configurations. So this is done, which is 1, then this is 2, this is 3, and this is 4. And we've seen that the part 1 or the configuration 1 was current amplifier. It means it gives you a gain of output current divided by input current. So this is your input current I in. You have an output current I out that flows through this load. Then this is applied, that current is applied to this feedback network indicated by letter G. And the output of this feedback network is a current that is then summed with the input current at this node. Okay, so it's a kind of current amplifier where the output quantity is current and the input quantity is also current. So that's a 2-port network configuration. Now let us focus on the second part, where the input is voltage that is applied to the input side. There is a gain block A, and the gain block A would be the output here is the I out again. So I out divided by VI. This is your VI will be the gain. And this amplifier is called as transconductance. Why transconductance? Which is the ratio of output current divided by the input voltage, I over V. Now this current I out is flowing through the load RL, then that is applied to this network Z, and the output of this network Z is the voltage, let's say a feedback voltage. Okay, so feedback voltage, the input of this feedback block is I out, and the gain therefore will be output divided by the input. So that's the definition of Z here. And you see now this feedback network is acting as a resistance. Okay. Okay, so because it's the ratio of voltage divided by the current. So now this voltage VF and the voltage VI are basically subtracted at these two nodes. So the output that is being fed to the amplifier is the difference between VI and VF. So here you have VI minus VF. That is why we say that. Okay, so that is about second configuration. Now look at the third part. Again, the input is the current I in, and you have the gain block A that gives you the output. Here is what is the output? Output here is now the voltage actually. So the voltage V out is being actually produced across the two terminal, or let us say across the load resistance RL, and that voltage that is at the two nodes right here is being fed to this block, which is a feedback network, and the input here is V out, and the output of this block is IF. That is, so therefore Y equal to IF divided by V out. So the gain of the feedback network, this is the forward block, this is the reverse block. So gain of the feedback network is characterized by the ratio of current over voltage. So it is called as conductance. transconductance. Okay. However, the forward gain, which is from input to output signal path, is A equals to V out divided by I in. Therefore, this this third configuration is called as trans resistance amplifier. Okay, and now look at this. This is the input current IN, and you have an feedback current IF that is being summed at this node. Again, you have I in minus IF that is going, the error or the difference between the two currents is going inside the amplifier block, which is the forward feed forward block. Now, final part, fourth plot. The input is V in that is applied to the forward block V in gain, and the output again here is the V out, which is basically the voltage across the load resistance RL, and the gain therefore is called as V out divided by V in. This is nothing but case of voltage amplifier. And you see that that voltage is becoming an input to this feedback network indicated by the block H, and the output of it is Vf, which is then subtracted with the input voltage V in. And now this new voltage here is basically V in minus Vf, which is just the same case as the second configuration. Okay, here the ratio of Vf divided by V out is the transfer function of the feedback network, that is H. So we have seen four cases. First one is current amplifier, second one is transconductance amplifier, third one is transresistance amplifier, and the fourth one is voltage amplifier. In the block diagram form, you basically say that this is your input. Let's say you have an input here, and then you have a positive sign here. There is a negative sign here because there is a subtraction. Now you have this forward current block, which is the gain of the amplifier, and then you have the output of this amplifier. Then you basically take the portion of the output and try to feed back it with the some network made of passives, and that is how you actually have this one. Okay, now you have this, let's say V or I here, you have V or I here, you have V or I here. So based on out of the four configurations, you can have that. Here also you have V over I. Okay, and that's how you have a case of negative phase. Here, the here at this node, actually, you have a error between the input signal and the feedback signal, or you can say that the difference between input and the feedback signal. So the advantage of using the negative feedback is that you have an improvement in the linearity and the reduction in the distortion. Therefore, you have a bandwidth improvement. Your input and output impedances of a network can also be improved. So now we talked about the negative feedback. What if I have a positive feedback? So it means I am adding the signal from the feedback network with the input signal. So that means I will have the addition here, not the difference between the two signals. That kind of feedback is called as positive feedback, which is employed to build an oscillator circuit. Okay, so I think we've comprehensively understood four classes of the feedback amplifiers. Hope you understood this video. If you are new to it, refer to the first part. This is second part. And wish you happy learning. Stay tuned for more engaging contents like this.